fundamental theorem of calculus. Now, doesn't that sound important? Grab you guys up. Where's the camera? Where's my screen? Maximize it. All right, so this is section 5.4. Moving right along through this book. Section 5.4, the fundamental theorem of calculus. We only have like 4 sections left to cover in this semester. Y'all realize that? Is that right? 1, 2, 3, 4, 5. Okay, the fundamental theorem of calculus. And really it comes in 2 parts. And what the fundamental theorem of calculus is really going to do for us, okay, is it's going to teach us how differentiation and integration are inverses of one another. So what it does is it shows us the differentiation, that's a difficult word for me, differentiation and integration are inverses of one another. One undoes the other. Inverses of one another. So that's kind of the whole goal of this section. Now it starts off talking a little more about the mean value theorem. I guess the notations may be a little different. It doesn't seem like a whole lot new here, but I can show you a little bit of an interpretation that will make it seem a little different than what we've already done, but it's very similar. And if we go back to remembering what we did do with the average value theorem, was remember the average value was really the average height of the function. So when we did this was really the average vertical height of the function over some set interval. And so it equaled the total area under the curve divided by the total width, or the interval length for which you were integrating. So, height is area divided by width, which is exactly what we're doing. But as we're working in calculus, we know that the area under the curve is to integrate from a to b of f of x dx, if you're looking between the values of a and b, and then divide it by width, where width is b minus a. Well, this is better written as just 1 over b minus a times the integral from a to b of f of x dx. And that's the final notation they give us. Now, when you look at this, it really looks exactly the same, but if you look at the new version of this in the textbook, the new kind of theorem written again with definite integrals, it's mentioned as what they call Theorem 3, which is on page 356 of the Thomas textbook. No, it's not. That is not right. Where is it? It's not on page 356. It's section 5.4. I will have to back it out. That one. Here it is on page 274. Where did I get 356? 274. And here it is. And it says the mean value theorem for definite integrals says if f is continuous, now it can't be jumping around on us, alright? If f is continuous, then at some point c, your mean value or your average height will be 1 over the width times the area under the curve, which is really what we've already defined. Here's a relatively good figure over here where your curve is the blue line, and really the area under the curve is the blue. And if they said the average height, the vertical height of this function is approximately right here, and then they took that height times the width, which would create this like pink box, then they're saying that that would be the average height of the function. Actually turns out to also be the average area under the curve. So the average height, if you multiply both sides of this thing times the width, then you're going to get that it actually turns out to also be the average area under the curve, would be the area computed with the height of the average value of the height function. So it's a really interesting diagram. where the average area is computed, it overdoes it here with the pink area, but then it's not catching the blue area. So if you kind of see that the pink area and the blue area are equal, then the area under the curve is going to be equal to this rectangle as it is underneath the curve. So that's a really good visual of this. Really good visual. So if y'all want to write that theorem down again, it says if f is continuous, and now when we integrate, it doesn't have to be continuous. Remember, it's a break. When we're looking for the mean value, then yeah, f must be continuous on our interval from a to b. And we're saying that f of c, the height of the function, the average height of the function is 1 over b minus a, 1 over the width, times the area under the curve. Okay, so an example of applying this, which will come very naturally to you, is if it says find the average value of f of x when f of x equals 4 minus x on the interval from 0 to 3, and then also determine where f takes on that value. In other words, what is the x value at which f is at its average height? F is the average height of the function. What is the x value where f takes on that average value that you determine? Okay, so also determine where f takes on that value. This is your x value where f is an average. Okay, and that's that question. All right, so if your f of x is 4 minus x, and if your width of your function, not the width of your function, the width of the interval is b minus a, it'd be 3 minus 0, which is 3. So to evaluate or to calculate the average height or the average value of the function, it's 1 over b minus a, the integral of f of x dx from a to b. So this turns out to equal 1/3 the integral of 4 minus x dx. I'm going to run out of space on this piece of paper from 0 to 3. I'm not going to have enough room. Should have realized that. So this ends up being 1/3, and when you integrate 4 as a constant, it's 4 times b minus a, which is 3 minus 0. That's like your f. Oh, we don't know this. Forget that. Okay. Whoops. Okay. Minus, and then the integral, when you integrate x, remember that's that b squared over 2 minus a squared over 2. So this is going to be b squared over 2 minus a squared over 2 when we are integrating x. So this isn't going to fit. This is 1/3 now times 4 times 3 minus b squared over 2. B is 3, so this is 9/2 minus 0/2. And if you clean all this up, this will equal, wave the magical wand, 5/2 because of lack of space. And it turns out to equal 5/2. So the answer to the first part of the question is, what is the average value of f of x? What is the average height in the interval of 0 to 3? Well, the average height is 5/2. So the average, we can go here, the average height is 5/2. That's like the part A of the question. The part B is to determine where f takes on this value. Where does the function equal 5/2? So to do this, you set your average value equal to the function itself. To find the x value at which the height is 5/2. To find the x value at which the height is 5/2. So maybe you should write this. This is the x value where f of x is a height of 5/2. It's that simple. Where the y value is 5/2, what is the x? So now if I subtract 4 off of each side, equaling negative x. This would be a negative 3/2 equaling a negative x, or x equaling 3/2. So that is the x value at which f has an average height of 5/2. So if we were to graph it, the two things you found out here, if you go back to this simple diagram, you found the x value, the c, at which the vertical value was an average. So you found the c, or the x value, at which f of x was at its average height. So I guess that's a little bit of an expansion on using the mean value theorem with our function. Okay, so there's our two answers. You got the average value, the average height of the function, and you have the x value at which that function is at that average height. Okay. And this one, honestly, I could graph it. This is just 4 minus x. If you wanted to graph 4 minus x on the interval of 0 to 3, we could do this very easily. 1, 2, 3. At 0, you're at a height of 1, 2, 3, 4. At 1, you're at a height of 1, 2, 3. At 2, you're at a height of 2, and at 3, you're at a height of 1. This is your graph, because it's just a linear graph. Okay, this is your f of x equaling 4 minus x. So we're saying the average height of this graph between 0 and 3 is occurring at 5/2, which is 2.5. Is it 5/2 or 3/2? No, it's the height. Okay, where the x value is 3/2. There you go. Your x value is 3/2, which is 1.5, which is right here. So if you go up to here, this is the ordered pair, 3/2, 5/2, which means that 5/2 is the average height of the graph. And if you were to draw your box, then the value of the area under the entire curve would be equal to the value underneath the box. Well, that's a really messy mess that I just made there, but I'm trying to get an image across to help you understand that material. So the mean value is pretty cool. Okay, pretty interesting stuff. Okay, so that's how they start this section, and then they actually move into the fundamental theorem of calculus. So let's get into the actual fundamental theorem of calculus, and it will come in two parts. The fundamental theorem of calculus. Let me move the camera up. Okay, then they actually come into, and it will come in two parts. So let's go ahead and just put on here that this is part 1 of the fundamental theorem of calculus. And what it says is, it says if f is continuous, okay, if your function is continuous on your interval from a to b, no breaks, no vertical asymptotes, then f of x, and when you see the capital F, that's your antiderivative, is equal to integrating your original function. Okay, your antiderivative can be integrating the original function f. And the capital F of x will also be continuous. Okay, on a to b. So your f of x, your little f of x, and your capital F of x, which is your antiderivative, are both continuous. And not just continuous, but also differentiable, meaning there are no cusps in this on your interval a to b. And its derivative is f prime of x is equal, the derivative of the antiderivative takes you back to the original function. The derivative of the antiderivative returns you to the original function, which is also the derivative of the antiderivative, if the antiderivative is equal to this integration, is d dx of the integration function. Okay, so this guy here, when you integrate, that gives you the antiderivative. And the derivative of the antiderivative is the original function. The derivative of the antiderivative is the original function. This is also the derivative of the antiderivative. So you can write the words, this is the derivative of the antiderivative. Okay, the derivative of the antiderivative is equal to the original function. The derivative of the antiderivative is undoing what was being done. So in other words, we kind of look at it, here's the antiderivative. You take the derivative of the antiderivative, it gives you the original function. Then you take the derivative of the original function, which we claim to be like velocity. Then you take the derivative of the derivative, and that's acceleration. So when you're going down this process, you are taking the derivative. But if you're going up, then you are integrating. Okay, if you're going the backwards direction is integrating. As you take the derivative, you're taking the primes or whatever, but you integrate, you reverse the process. So they're inverses of one another. They're inverses of one another. Okay, so then it goes on to say, well, I guess that's okay. But some of the problem is what does the t variable have to do with anything? Why are they throwing another variable into the definition? Well, when they're doing this, remember when you integrate, you're finding the area under the curve. So if you're looking at the curve, which is f of t, then this is t, f of t. Your x-axis is t, and your vertical is f of t. So if you have some graph here of f of t, then you're finding the area of the curve between a and some other number, which we're going to call x, so that your f of x is in the variable x. And so when you do this, you're finding the area under the curve between a and x, which is throwing you back into the x variable. So then when you integrate from a to x, the x must be your upper limit. And your upper limit must be x. The lower limit is not as critical because the lower limit is just a number. But the upper limit is critical that it must be x in order to put our function back in the variable of x. Okay, so this is the area under the curve. But if this is taking the derivative, if you take the derivative of the antiderivative, it throws you back to the original function. So a little confusing. I think the best thing to look at is this, okay? Take the derivative versus the antiderivative will reverse the entire process. Okay? So let's take a look at some examples. Remember, d dx is taking the derivative. Okay? So d dx is the derivative. So if you're taking, this is saying take the derivative of something. d dx is take the derivative of something, you're going to put right by the d dx. Well, if you take the derivative of the antiderivative, if you're taking the derivative of the antiderivative, it returns you to the original function. The derivative of the antiderivative returns you to the original function. So this becomes cosine x. The derivative kind of wipes out the integral symbol and returns you back to the original function. Okay, so here's another one. Suppose you're doing d dx of even 0 to x. The lower limit, the constant, which is the lower limit, does not affect the value of the function, the original function. So if they give me something like 1 over 1 minus t squared dt, your first thought is, I don't know how to integrate that, but you don't care because you're taking the derivative of the antiderivative. The derivative is reversing that integral symbol. So your derivative is reversing the integral symbol, which is going to send this back into the variable x. Okay, this is the derivative of the integral. It's reversing itself. The derivative of the integral, undoing what's being done. Okay, so suppose they say, now this one's a little bit different. They say take d, well the notation's a little different. Taking this straight from the book, dy dx, if y equals the integral from x to 5 of 3t sine t dt. Now we have an issue here because your upper limit is not x. Okay, that's not good. This upper limit right here needs to be x. There you go. And to make it negative, you reverse your upper and lower bound, or your upper and lower limit. So if you reverse these, then your original function is the negative of 5 to x of 3t sine t dt. So we've not taken the derivative of the antiderivative yet. But the minute I write this, the minute I take, and I'm kind of low on my page, so I'm going to have to move back up. You keep going down your page. The minute I take dy dx, that is a d dx of y, where y is the integral of 5 to x of 3t sine t dt. This is a negative, not a minus sign, but a negative. Maybe I should put a negative 1 there. Okay, it's a negative because we reversed or we switched the upper and lower limits, which makes it negative. So this is the derivative of the antiderivative, which returns us to the original function, which is just 3x sine x. But that negative is there because we reversed the upper and lower bound. Uh-oh, I'm off the screen. Taking the derivative of the antiderivative. Okay, it's the notation, okay, but the words over and over again you're hearing me say is the derivative of the antiderivative. The d dx is the derivative, the integral is the antiderivative, which spits out the original function. You're reversing the process. You're reversing what the antiderivative is trying to do. You're saying, don't take the integral of this thing, back it out of the process, get it out from in the integral and pull it back out because we're going to reverse it. Okay, so what is the theorem? What is the fundamental theorem part 2? Okay, and this is the part we use extensively. Okay, you need to memorize this. It's very easy to memorize. You'll get very quick at this, and you will use this repeatedly through all calculus. Okay, what it says is how to integrate without being limited to what we saw in the last section with the standard formula for integrating x or the standard formula for integrating x squared kind of stuff. So this is going to generalize it so we can always integrate really without those formulas. So if we are integrating a function, finding the antiderivative, then remember the antiderivative is capital F. So when you get the antiderivative, you take the value of the antiderivative at the upper bound minus the value of the antiderivative at the lower bound. Now, There's a lot of notation here. Remember, the capital F function means you know how to integrate this thing. You're going to integrate it, and when you do, you're going to evaluate it at the upper bound minus at the lower bound. So how do we do this? What is the process for doing this? The first thing you do, step 1, is to integrate, which means find f of x. Find the integrate. And when you come up with it, then step 2 is to calculate f at the upper bound and f at the lower bound and subtract upper minus lower, which is what you're doing with that theorem. This is not difficult. Sometimes there's a lot of little numbers with negatives that you have to be very careful with. There's details, but it is not difficult. So here's some examples. Okay, there's a lot of notation going on. Now we're going to show it really in the process. Okay, suppose they ask me to integrate from 0 to pi, not a to b or a to x. It's 0 to pi. We have actual values for our lower and upper limits. And we do this for cosine x dx. Well, the first thing we say is, what is the integral of cosine x? Well, the integral of cosine x is what? Sine x, right? And here's the notation. The integral is sine x. And then you put this little square bracket, and you're finding this between the upper and lower limits of 0 to pi. That's your notation. When you integrated, your antiderivative was sine x, and now you're evaluating the antiderivative between the bounds of 0 and pi. So the way you do this is you take the antiderivative of the upper limit minus the antiderivative of the lower limit. So now you're looking for f of b minus f of a. Well, f of b is the upper limit, which is, of pi. So this is sine of pi minus f of a, which is going to be sine of 0. So the top minus the bottom. Sine of pi is 0, and sine of 0 is 0, which equals a grand answer of 0. How is it possible that my area could equal 0? Spit it out, okay? Because it does something. Okay. There you go. There he said it right. Because some of the area between 0 and pi is positive and some of it's negative. If you graph cosine x, okay, this is cosine x's graph. If you were to graph cosine x between 0 and pi, okay, at pi halves it equals 1. Is that right? No, it's 0. Okay, so at 0 it equals 1, at pi halves it equals 0, and at pi it equals negative 1. So it's a wave that looks like this. Now, if you're evaluating the area between this curve and the x-axis, and we normally say the area under the curve, but really between the curve and the x-axis, then here it's positive because your y values are positive, and here it's negative. And they're equal amounts because this is a symmetrical curve. So when you add the positive to the negative, you get 0 area, algebraically. So when you integrate, it's possible to get a 0. And that's why that's the visual of why that works like that. Okay, very good. The areas, one was negative, one was positive, and it zeroed itself out. Okay, here's another one. Suppose we want to go from a negative pi fourths to 0 of secant x tan x dx. You're finding the antiderivative, then you're going to evaluate it from your upper limit and your lower limit. Well, the antiderivative of secant x tan x is secant x evaluated between a negative pi fourths and 0. Now, the pattern is to do the antiderivative at b, the upper limit, minus the antiderivative evaluated at the lower limit, negative pi halves. So this is secant of 0 minus secant of a negative pi fourths. Well, secant is 1 over cosine. Cosine at 0 is 1, so secant of 0 is 1. Secant of a negative pi fourths is 1 over cosine of pi fourths in quadrant 4, which is still positive, which is the square root of 2 over 2, right? So this is 1 over the square root of 2 over 2. So this is 1 minus 2 over the square root of 2. This is confusing. Which is the square root of 2 over 2 minus 2 over the square root of 2, which is the square root of 2 over 2 minus the square root of 2. There's a lot of ways we could answer this one, people. I guess we would leave it like that. I'm not certain which is the better of two evils or the worst of two evils. Something like that. Okay. Now the next one's going to be a little bit hairier. These are pretty simple. Okay, these are just trying to really prepare you for when they do get a little bit messy, I guess you could say. Now I've got to look at this. Now that I've come up with this example, I've got to look at it. Have we ever integrated the square root of x in this class yet? Do we know how to do that? It's so hard to go back and remember. Do we have a formula for the square root of x? But we don't know that yet. We don't know that yet. How to increase it by 1 and divide. We do know how to do that. Do we know how to do that? Okay. Yes, okay, then we can do this. I'm sorry. It's hard for me to remember what we can and cannot do. Okay. Okay, what if we have 3 halves times the square root of x minus 4 over x squared dx? This one's a little bit messy. It's not hard, but it's going to be messy. Okay, so the first thing I would do is split this into 2 integrals. So I would let this be 3 halves the integral from 1 to 4 of the square root of x minus 4 times the integral of 1 over x squared dx. I'd split it up. And then when I got ready to integrate, I would do the first one. What is this? Okay, well, 3 halves times the integral from 1 to 4 of x to the 1/2 dx equals, what is the integral of x to the 1/2? 2/3 x to the 3 halves, right? So this is 3 halves times the integral of x to the 1/2 is 2/3 x to the 3 halves. And you're evaluating this from an upper limit of 4 and a lower limit of 1. So this equals 3 halves times, put the 4 in here first, 2/3 times 4 to the 3 halves power minus the lower limit, 2/3 times 1 to the 3 halves power. This is your f of b minus your f of a, which is put the 4 in and then put the 1 in to the antiderivative. So this then equals 3 halves times 2/3 times 2 cubed is 8, which is 16/3, right? Do y'all agree? I got 16/3. What did you get? This is 16/3, right? Not yet. You got to move it on both. Okay, on all of it. Okay, you're right. Okay. I see what you're doing. But he's with me. He's with me. He's following me and you're not. Okay. This is what? 14/3. Then the 3's go, and this turns out to be what? 7? There's half of it. There's half of it. Okay, then the lower half here, and I'm just going to leave the subtraction there. The lower one, or the second one here, is 4 times the integral of what? X to the negative 2 dx. And I'm going to drop a little bit on the page. So this is going to be 4 times, when I take the antiderivative of x to the negative 2, it becomes negative 1 x to the negative 3, right? Evaluated from, get my bounds on here, 1 to 4. Get my upper and lower limits, 1 to 4. Wait a second. Did I do something wrong? There you go. Yeah, it's a negative 1. That is a weird-looking expression. So this is 4. Let me redo this. This is what? Negative 1 over x, right? Okay. So this ends up equaling f of b minus f of a, which is 4 times negative 1/4. Okay, this is f of b minus f of a, which is where you put the 1 in, which is a negative 1 over negative 1, right? You put the 4 in, and you put the negative 1 in, and you're subtracting a negative value. Your subtraction is the f of b minus the f of a. That's where that subtraction is coming in. Then you're plugging in the upper and lower limits. Yeah, okay, this is a positive one. I'm getting carried away, huh? That's a positive. I'm getting a little carried away here with all these negatives. So this is 4 times a negative 1/4 plus 1, right? So does this equal 3? This should be negative 1/4 plus 4/4. Right, a negative 1/4 plus 4/4, which is 3/4. So this equals 3. Whoops, I shouldn't square it off. Equals 3. So now the answer to the ultimate question way down here is that I take the 3/2 from 1 to 4 square root of x, which turned out to be 7. I subtract the 4, 1 to 4, 1 over x squared, which is 3. So our integral value is a grand tally of 4. You're just straight algebra integrating. Okay, so evidently we had area above the curve and area under the curve because we got a negative. Did we get a negative? No, we didn't get a negative. We did okay. Yes?
Okay, so just really fast.
Mm-hmm. Uh-huh. Mm-hmm. It was a given, way up here. That was given. And so this was, I knew this was going to be really ugly, so we broke it into 2 parts. We just did this part, and then we came back and did that part because it was really a lot of little numbers all over the place with subtraction and negatives. And right here, okay, it's x to the 1/2 when you integrate it, right? There you go. You add it by 1, and then you divide by that number, right? Remember that? You increase your exponent by 1, and then you divide by that number. So this equals 1 over 3/2 x to the 3/2. And then 1 over 3/2 is 2/3. So you're having to take a complex fraction and play around with it a little bit. What a mess! There's not a whole lot of anything difficult on that page, but it looks terrible. Okay, it's just called be careful, because it's really frustrating when you make a minor mistake. And splitting that into 2 parts is just almost a necessity to get that right. Okay, it's just really kind of difficult. Okay. That's ugly. Good grief. Oh, you are smart. You can do it. Okay. Where's this go? All right. Y'all are smart. Y'all can do this. Let me see what my next letter needs to be. Capital D. Okay, so now we've done some practicing. We've done some examples of integrating by that formula, more or less, which is the second part of the fundamental theorem of calculus. Okay, so now what we're going to get into is talking a little more about the area under the curve. And we've kind of introduced this just in talking during this lecture. But if we're integrating, we're just coming up with numbers. But if we're looking at the graph and we really want to know area, we really shouldn't have negative area. We can have a negative value for an integral, but really, if we're talking about area under the curve, area should not be negative. So if you have a function, like we had earlier, the cosine function that goes like this, okay, where you have area up here and you have area down here, when you just integrate, you're going to get a negative and a positive area. When you integrate, this is going to be a positive amount above the curve. But when you integrate here, it's going to be a negative value. Because when you're under the x-axis, algebraically, your y value is negative. And when you multiply a negative times a positive, you get a negative result. So when you just integrate, you're going to get negative values. But when we actually want to know the true area, rather than just to integrate, we need to take the absolute value. Okay, if you really want to know the true area, then you need to take the absolute value of anything that comes out under the curve. So in this case, if we have numbers, this was what, 0 and pi halves and pi. If I really wanted to know the area under the curve versus just integration, I would integrate from 0 to pi halves of the cosine function, and then I would add it to the integral of pi halves to pi of the cosine function. Well, whatever value I get, wasn't it 1? Didn't we do it with a 1? This came out to be 1, and this came out to be negative 1, right? So when you integrate, you get 0. But if you really want to know area under the curve, you would say 1 plus, and you would take the absolute value when the area is under the curve, or when the area is a negative value. Okay? Take the absolute value when you get a figure which is negative representing area. So the area under this curve is 1 plus 1, which is truly 0. When you integrate, you get 0. When you want to know the true area under the curve, you get 2. So when you integrate, there's two things that happen. If they say integrate, you get whatever you get. But if they say find the area under the curve, you need to take the absolute value of any area which is under the x-axis, so you come up with a true value. All right, so here's some examples. So now what you have to do is figure out where is the curve above the x-axis and where is the curve below the x-axis, so I know where I'm going to have to take the absolute value. So if you take a look at this one, they say graph f of x equaling sine x from 0 to 2 pi. Then they want me to do two things. They want me to compute the integral, which is just integrate, and there'll be positive and negative, who cares. And then they want me to compute the area under the curve. Okay, so both of them. Find both. Just integrate it, but then actually integrate it and find the area between the curve and the x-axis. So if we just compute the integral alone without thinking area, then we would simply integrate from 0 to 2 pi of sine x dx. That's just sheer algebraic integration. So when you integrate sine x, you get negative cosine x, evaluated from 0 to 2 pi. So then when you do the f of b, the antiderivative at the upper bound minus the antiderivative at the lower bound, then you're going to get a negative cosine of 2 pi minus a negative cosine of 0. Well, cosine at 2 pi is 1, so this is a negative 1. Cosine at 0 is 1, but that's a negative of a negative 1. So it becomes a negative 1 plus 1, which is a 0 amount. So when you integrate it, you get 0. So at that point, you're thinking, okay, this curve, whatever it looks like, must have had the same amount of area above the x-axis as was below the x-axis in order for it to zero itself out. And it did. So if you want to graph it and take a look at it, we know what the sine curve, it's a wave. Okay, this is sine x. It starts at 0, then it goes to pi and 2 pi. It goes up to a height of 1, then it goes down to a height of negative 1 or an amplitude and comes back. So as we can see, between 0 and 2 pi, the area above the curve is equal to the area below, or the area above the x-axis is equal to the area below the x-axis. And yes, it does make sense that the area would be 0 or the integral would equal 0 because it takes the positive and the negative and zeroes out. But if I really want to find the true area, then I would need to integrate it from 0 to pi. And then I'd want to integrate it from pi to 2 pi. And when I integrate it from pi to 2 pi, what am I going to have to do? I'm going to have to take the absolute value of it there because that's where it's under the curve. That's where it's going to be negative. So I integrate from 0 to pi, where it's going to come out a positive number. And then when I integrate from pi to 2 pi, it's going to be a negative number. And I'm going to take the absolute value of this one in order to get true area so it doesn't zero out. Well, I hope I made enough room here. So the integral of sine x, we already said, was a negative cosine x evaluated from 0 to pi. And here it's a negative cosine x evaluated from pi to 2 pi. Yeah, there's more than one way of doing it. So this would be negative cosine of pi minus a negative cosine of 0. This is going to be a negative cosine of 2 pi minus a negative cosine of pi. So this becomes cosine of pi is negative 1, so a negative of a negative 1 is a positive 1. Cosine of 0 is 1. Cosine of 2 pi is 1. This is a negative 1. Cosine of pi is negative, so a negative of a negative makes it... How many negatives can we get? Cosine of pi is negative 1. This is a positive 1. So this equals 2 plus a negative 2, but we're going to take the absolute value of the negative 2 because we're looking for area. We don't want these negative values when we're talking about area. So then it becomes 2 plus positive 2, which gives me a grand total of 4 for the area between the curve and the x-axis, always looking at it in a positive value. All those negatives, you've got to be so careful. Okay? It's all the negatives that you have to be so careful with. So careful. And I am at the very bottom of my page. Let's do another one. This one won't have so many negative 1s in it. Okay. Suppose we want to calculate the area. It doesn't say just integrate. It says calculate area. So it doesn't just say integrate. This means make everybody positive. Calculate the area bounded by the x-axis and the parabola y equaling 6 minus x squared. Calculate the area bounded by the x-axis and the parabola y equaling 6 minus x squared. Well, that's a parabola who is concave down. We really need to graph this thing. Okay? Yes, right. We need an interval, but the interval is going to be determined by where it's crossing the x-axis. Okay, by the zeros of the function. Okay, so if I'm going to graph this thing and I know it's concave down, I need to know the x-intercepts. So if I'm going to graph this y equaling 6 minus x squared, I want to know where the x-intercepts are. To get that, I set this thing equal to 0. Well, when I do this, I'm going to have to factor, so I'm going to reorder this as negative x squared minus x plus 6. Okay, I'm finding the zeros of the function, which are the x-intercepts. So this is a negative 1 times x squared plus x minus 6, which is a negative 1 when you factor it, of x plus 3 times x minus 2. So then you get your zeros of your function. You cannot set negative 1 equals 0, but x plus 3 equaling to 0, x minus 2 equaling 0. Your x-intercepts, or your zeros of this function, are occurring at a negative 3 and a positive 2. So when you graph this thing, you have a 0 at a negative 3 and a 0 at a positive 2. You know it's concave down because it's a negative x squared. I don't know how high it goes. I don't really care. It's going to look something like this, I assume. So now when the question says calculate the area bounded by the x-axis and the parabola, bounded, the only place it's bounded is in here. The rest of it's heading out to negative infinity, right? Here's where the curve is bounded by the x-axis. So you're looking for that area of the curve, and we're blessed that it's all above the x-axis, so it's all going to be positive. So when you're asking what is the interval that we're integrating over, you're going to integrate from a negative 3 to 2 of your function 6 minus x squared dx. That's what you're going to integrate. That's going to give you area. It's going to always be positive. You don't have to break it into 2 or 3 parts. So when you do this integration, it turns out to be 6x minus 1/2 x squared minus 1/3 x cubed, evaluated from negative 3 to 2. We all good? So now the upper bound, the f of b, the antiderivative evaluated b where b is 2, is going to be, put the 2 in, 6 times 2 minus 1/2 times 2 squared minus 1/3 times 2 cubed, that's f of b, minus f of a, which is to plug in the lower bound of a negative 3. So this is going to be 6 times negative 3 minus 1/2 times negative 3 squared minus 1/3 times negative 3 cubed. This better come out positive. This better come out to be a positive value. This is what? 12 minus 4/2, which is 2, minus 8/3. This is a negative 18. minus a 9/2. Here's 3 is 9, and 3 is 27, plus 27/3, right? So this becomes 12 minus 2 is 10. So this is 30/3 minus 8/3. Golly, I need to put everything in sixths over here. Ugh. Oh. If I want a common denominator of 6. Oh no, there's no back trees in this calculator. I think I have another one. I thought. Okay, so this is what? A negative 108 over 6 minus 3 times 9 is 27 over 6. 27 times 2 is 54 over 6. Good grief. So this is 22/3 minus, what's all that mess? 108 and 27 and 54. Should I get a negative 81 over 6? Isn't that right? So this is 6 times 108? Okay. So this is, what, 44 over 6 plus 81 over 6? Are we done yet? There is the area under the curve bounded by the x-axis. The area under the parabola bounded by the x-axis. It is not difficult, but my goodness, you have to be so careful with your numbers. So careful. Okay, maybe I'll just set the next one up. Here's another one. Find the area of the region. Now remember, if it's area, you better figure out where it's negative and where it's positive. Of the region between the x-axis and the graph of f of x equaling x cubed minus x squared minus 2x, and you're looking in the interval of negative 1 to 2. Now, when you see the word area and it doesn't just say integrate, you better be thinking, is there any place in this graph where it's going under the x-axis where I'm going to have to take the absolute value? Am I going to have to split this integration into parts according to where the graph is under the x-axis? So you better come in here and you better graph it. And what you really need to know is where you're crossing the x-axis, where it's dipping under the x-axis. So if I want to graph y equaling x cubed minus x squared minus 2x, it's a third degree function. It's going to have an end behavior of up on the left and down on the right. I know the end behavior is up on the left and down on the right. It's going to be crossing that x-axis how many times? So I need to find out how many x-intercepts there are. So if I want to find the x-intercepts, which we also refer to as the zeros of the function, I set the y value equal to 0. Pray this thing factors kindly for me, and it will. and I come up with x equaling 0, x minus 2 equaling 0, x plus 1 equaling 0, and I have 3 x-intercepts on this cubic function. So some of it's going to be above the x-axis and some of it's going to be below it, and to find those upper and lower limits of my integrals, I'm going to have to figure out where. Knowing it's a cubic function, knowing my end behavior, a -1, a 0, and a 2. It's going to go up, then it's going to come back down, and then it's going to go back up. Something like that. Of course, you can pick up your handy-dandy calculator and see it. But at this point, you know that you're going to integrate this function first from -1 to 0, and that's going to be positive. That's not a problem. Then you're going to integrate this function from 0 to 2, and this sucker is going to be negative, and I'm going to have to take the absolute value of it. This part is supposed to be negative. It's going to be negative. So to get the area, I'm going to have to take the absolute value of that half in order to get the area under the curve rather than just the integration of the value under the curve. Now this is a lengthy thing. I don't think I'm going to do it all. I'm going to lose you. But when you come in here to do this, this is how you're going to set it up. Okay, so this is going to be 1/4 x to the 4th minus 1/3 x cubed minus x squared evaluated from -1 to 0. And then it's going to again be 1/4 x to the 4th minus 1/3 x cubed minus x squared evaluated from 0 to 2. And this part, you're going to have to get a value which will be negative, and you will have to then take the absolute value of that in order to get the true area between the curve and the x-axis from -1 to 2. We couldn't find the area to the left of -1 or to the right of 2 because it's not bounded. Okay, it's not bounded, so we would not be able to do that. But I'm going to put etc. Lots of work for you to do someday if you feel like it. You'll get your practice in your homework. Okay, how's that? Believe me, you will. And you will be frustrated if you're not extremely careful. You don't want to work too quickly through this or you're going to be mad. All right, so let's take a look at some stuff and there's some really neat examples briefly. Just kind of look at it in the textbook, which I'm hoping I'm going to find some of it also in my math lab. I haven't created your homework, but I will create it this evening. Man, is this part E? It is, right? Okay. I'm just going to show you some brief examples, and I do pray that this is in my math lab because these are really neat. But in the textbook, I want to at least show this to you. Numbers 45 through 48 on page 283. Just take a look at this. These are very good questions, and I hope that it made it into the software package. But regardless, I want you to see it. 283. Because I got to look at it and thinking, what in the world? Look here at number 45. Focus, little camera. Okay, I did it. Okay. Find the area of the shaded region. Look at number 45. The shaded region is not under the curve. Right? How in the world are you going to do that? What is it? Would it be 2 pi minus the integral of 1 plus cosine x from 0 to pi? Think about that. Is the answer set up for number 45 is the area, the blue area, is it 2 pi minus the integral of 0 to pi of that 1 plus cosine x dx. Look at that. Is that right? Where did I get 2 pi? There you go. Okay, if you look at the diagram, something like this, then they have this little box here, right? Why is it so? Okay. And this point here, this area, this length is pi, and this height is 2. Oh, it is. Why is 2? This height is 2, and that width is 2, and this height is pi. So the area of the box is 2 pi. Now the area under the curve is the integral from 0 to... Did you tell me wrong? You messed me up, didn't you? Shame on you. This is pi, and this is 2. Okay. Okay. There we go. Okay. Okay. Same difference. The area is 2 pi. Okay. This is 0 to pi of the curve. So if I take the area of the whole box, right? If I take the area of the whole box, am I on this camera? Take this camera back out. Zoom, get out. Back out a little bit, camera. Didn't do anything? Didn't do anything. Didn't do anything. Okay, so if I take the area of the box, shaded box, and I subtract the area under the curve, right? If I take the area of the whole box and then I subtract out the area under the curve, it'll leave behind what they want, which is that area outside the curve. So that's where you come up with 2 pi minus the integral from 0 to pi of the function 1 plus cosine x dx. It's very geometric. Okay, it's very geometric. Area of the whole minus area of the part gives you the remaining shaded region. Okay, really cool. Kind of fun. And then they do a little more of it, like this one, like number 46. You take the area under the curve from pi 6 to 5 pi 6, and then you subtract out the area of that little rectangle. Okay, you can do that. This one would be a little more difficult. This one, you take the integral from negative pi forced to 0, which is good, and this would be the area of a box minus the area under the curve. So you have to really play in 2 parts. Same kind of processing there. So there's a little geometry, really pretty creative questions right there on 45 through 48. Really creative questions. And then you can see this is the kind of stuff, the rest of the stuff you're going to see in your homework set. Okay. Now, right here, the questions are a little in reverse of the way the material was taught in the section. But here on number 33 through 40, they're telling you to take the derivative of y, which means take the derivative of the antiderivative. This is the derivative of the antiderivative, which is inversing, okay, reversing the antiderivative on numbers 33 through 40. Really interesting stuff. Okay, you are a little dead. Luckily, we're through with this section, so I'm going to pause or stop the recording. We'll take a break and come back and look at the next section.